this video, we're going to continue with the discussion where we stopped in the previous video on stability in linear time invariant systems. In the previous video, we have seen that initially we started with qualitative description or statements on the stability of LTI systems, and then we went into quantitative analysis of it, and we concluded saying that if the area under the impulse response curve for a system is finite, then we can say the system is stable, and the behavior or the nature of this g of t, which is nothing but the impulse response, is dependent on the poles of the transfer function. So finally, the stability definition from qualitative analysis came down to the poles of this transfer function. So now the location of the poles of the transfer function on the S-plane will give us a better idea about the stability. Let us start taking example transfer functions with poles located in different parts of S-plane and start analyzing how this stability is described. Okay, so to start with, I'm taking a transfer function which is like 1 over s plus 2. For this, if I represent the poles in the S-plane, it looks like the pole is located at minus 2, right? Now, if I see how the impulse response, which is nothing but g of t, anyway, we know this transfer function is g of s here, so the impulse response will be equal to e power minus 2t. Okay, if I plot this response, which is impulse response, it starts from 1, okay, it goes down and it tends to 0. Now if you look at this plot from the condition of stability, the area under this curve, okay, absolute function of this, and taking the area under this curve, the area should be finite. Of course, this function shows that the area is finite under this curve. And if you look at the stability quantitative or qualitative statement which we made, the second one, that the output should tend to 0, even that condition it is satisfying, we can say this system will be stable, right? Now if you take another example where it is 1 over s minus 2. Now similarly, if you plot that particular pole in the s-plane, we can say this is present at plus 2. In that case, if you see what is this g of t, g of t we can write it as e power 2t, taking inverse Laplace transform. Okay, now if you try to plot this plot, which is e power 2t, of course we have to multiply this with u of t, right, because we are taking unilateral Laplace transform. Okay, now it starts from 1, it starts increasing. Okay, now looking at that condition, the area under this curve should be finite. If you look at this, area will be tending to infinity as we integrate this function from 0 to infinity for sure. And the output is not actually tending to 0 as t is increasing. So it means the system will be unstable. Okay, and this system will be stable. These are the two conditions we saw related to if the system has a real poles on the S-plane. Okay, now let us take a case where we have complex conjugate poles. Okay, now say we have complex conjugate poles present on the left half of S-plane. Let's see how this will be. Now if you look at this value j omega, okay, let's say this is omega 1, and this real value, suppose say uh, minus sigma 1. Okay, now if we see the time response of this particular function which has this pole 0 configuration, okay, then the function we are going to have is, it will be something, okay, oops, it's okay, the function will be something like this. Okay, a sinusoidal function or a cosinusoidal function which will be tending to 0 as t tends to infinity. Okay, this envelope will be guided by this e power minus sigma 1 times t. Okay, so the real part of this is actually guiding the envelope of this. Okay, and this omega 1 will be nothing but, if you look at the time period here, suppose say t, this t will be equals to, okay, usually this omega 1 equals to 2 pi by t. Now if you take t here, okay, it will be 2 pi divided by omega 1. This omega 1 will determine this angular frequency, or here the time period. Okay, now let us take if this same complex poles are present in the right half of S-plane. Okay, then how does this look? Let me take the S-plane, okay, and represent poles in the right half. For this case, the sigma which guides the envelope is positive. In that case, we'll have a function like this. The envelope will be keeping on increasing, okay, and if we try plotting this, usually it will be starting from a very low value, say usually 0, something like that. Okay, it will be increasing. Okay, the output as t tends to infinity won't be converging to 0, instead it keeps on increasing, and we can say this system will be unstable. Okay, if the system has poles in the right half of S-plane like this, okay, complex conjugate poles, we can say the system is unstable. Here it will be stable. Okay, and we can see some more examples. Okay, uh, let us see other examples. Previously we have seen conditions where the complex conjugate poles present in the left half of S-plane, and in other case we have seen if these complex conjugate poles present in the right half of S-plane, whether the system will be stable or not. Now let us see if these complex conjugate poles are present exactly on the j omega axis, then how does the system behave? Okay, let us take this condition. In this case, let's take j omega 1, okay, and minus j omega 1. Now the impulse response for this particular system with this pole 0 configuration, anyway we don't have zeros here, okay, let's look at the poles. The output looks like a sinusoidal function or a cosinusoidal function. Okay, and the magnitude is going to be constant, right? In this case, according to the first condition of stability, the system's output is bounded for sure, right? It satisfies the first condition, but it won't satisfy the second condition. Second condition states the output should asymptotically tend to 0. But here we have a magnitude which is changing continuously and it is not tending to 0. Right? It is satisfying the first condition, but it is not satisfying the second condition. According to our definitions, this system is unstable. In such cases, we define a term known as marginally or limitedly stable system. This is basically, okay, we define this based on, depending upon the amplitude of the ultimate response, such a system may be treated as acceptable or non-acceptable. This situation is referred to as a case of marginally or limitedly stable system. So here we can say this is marginally stable systems, okay, or marginally stable system depending on the application which we are going to use. Let us see another case where suppose if we have these complex conjugate poles present on the geometric axis, okay, suppose they are in multiple in number at the same point. Okay, here you have two roots, here we have two roots at exactly the same point, say omega 2. Okay, this is minus j omega 2. In that case, the output response will be like this. Okay, the output response will be keeping on increasing as time progresses. Okay, as time progresses, this keeps on increasing. For sure, if we have multiple roots, okay, at the same point on the j omega axis, we can surely say that the system will be unstable. Okay, now let us see a condition where we have a pole exactly at the origin. Okay, let us see a condition like that where we have pole of the system exactly at the origin. So this kind of transfer function is nothing but a transfer function of an integrator block. Okay, for this the impulse response looks like this. Okay, the impulse response for this integrator will be output will be a unit step, which is nothing but the impulse response here. If you look at this carefully, it satisfies the first condition of stability, which says that the output should be bounded. Of course, the output is bounded here, so it satisfies the first condition, but it won't satisfy the second condition because the output is not asymptotically tending to zero, right? So if you take area under this curve, okay, as t tends to infinity, even though the output is bounded, you'll have the integral value to be coming out to be infinity. So now based on this condition we can say the system is unstable, but as we defined the marginally stable systems in the previous example here, right, in this case. So based on that we can say the system is marginally stable, okay, depending on the magnitude of interest which we are seeing and the application we are using it, right? Now if we have roots at the origin repeated, let's say I have two poles at this place, which is the transfer function is 1 over s square, then if I look at the impulse response, okay, it keeps on increasing. This is nothing but a ramp function. Okay, so this type of systems are unstable. Coming to this first condition, the output is not bounded, it keeps on increasing, so it doesn't satisfy the first condition. And of course, as it is increasing, it's not coming down to zero asymptotically, so it won't be satisfying the second condition also. For sure, this system which has this pole zero configuration will be an unstable system. Okay, looking at all the examples we have seen previously, okay, based on that we can make some conclusions here. They are like, if you take S plane, okay, this is right half of S plane and this is left half of S plane. Now if I have poles in the left half of S plane, then we have seen that the impulse response comes out to be decaying. It means the area under the curve is going to be finite and it satisfies both the stability conditions. And if I look at a system which has poles in the right half of S plane, it makes the impulse response to increase as time progresses, and it won't be satisfying both the conditions of stability of LTI systems. So we can generally make a statement saying that if we have poles of the system present in the right half of S plane, for sure the system is going to be unstable. Okay, and if you have all the poles of a system in the left half of S plane, the system will be stable. And now coming to this point of this j omega axis, where if you have a single root present on the j omega axis, okay, or maybe a non-repeated complex conjugate poles on the j omega axis, and the rest of the poles are present in the left half of S plane, then we can say the system will be marginally stable depending on where you're using it and depending on the magnitude it provides. Okay, when I'm referring to magnitude, suppose we looked at a case where we had a sine wave like this, right? And if the sine wave magnitude is suppose say 5 volts, and the application you are using it where the ratings of the output depending on the parameters you are using inside or the elements, the ratings are supposed to say 4 volts, then in that case if you use the system won't be stable because it's exceeding the ratings and it may burn out the elements in it. So we can say this is unstable depending on the situation there. That is the whole point of saying this depends on the magnitude you're looking at and depends on where you are going to use this. Okay, but in general, if you see any poles or single poles, I mean, which are not repeated at the same point, then you can say the system is marginally stable. Okay, so finally, if we have all the roots present in all the poles present in the left half of S-plane, we can say the system is stable. If a system has at least one pole in the right half of S-plane, we can say that system is unstable. And if you have a system which has all the poles in the left half of S-plane, but one or a non-repeated poles on the j omega axis, we can say the system is marginally stable. Thanks for watching the video, and if you have any queries or questions, send me a message and I'll reply for them. And please do comment below the video in the comment section.